Welcome back. This is data visualization, data 205N, week one. This is lecture number 2. I'm going to pick up where I left off last time, which was, if you recall, we went through a lot of different kinds of visualizations. That's just a tip of the iceberg of the different kind of visualizations we're going to see. Now I'm going to shift into a section called Truth Telling with Visualizations. This is actually chapter 9 in your textbook. That's why this week you have reading out of chapter 9, out of chapter 1 and chapter 9, because we think it's really important that you understand how you can mislead readers by incorrect visualizations. And very often a chapter will start with a data visualization makeover. This is an example of that. This is this week's makeover. Now, this is showing the box office revenue, gross revenue for the top 10 movies of all time. And on the left is the non-inflation adjusted number. And so the year of release is on the horizontal axis. The dollars in millions is on the vertical axis. And if you just took that chart on face value, you'd say that Star Wars Episode 7 was the highest grossing and Avengers Endgame was the next grossing, so on and so forth. The problem with that is that these were released in different years. And in fact, there were lots of movies that released back here that grossed a lot of money, but when we didn't adjust for inflation, they don't show up on the chart. So this chart on the right shows it's the same chart. The only difference is that we inflation adjusted the dollars. Now that's really significant. In 1951, right here, average price of a movie ticket was 53 cents. In 2020, it was 937 or 17 times more expensive. So you really do have to think about over a long range like that, where you're going from, 40 to 2020, that's 60 years. You really do have to think about adjusting for inflation. And when you do that, interesting thing appears. The highest grossing film of all time in inflation adjusted dollars is Gone with the Wind. And the next highest is Star Wars, not 7, but Star Wars 4. And so the point is that this is misleading. This graph on the left is misleading because it's not adjusting the dollars for inflation. This is much more meaningful because I have adjusted the dollars for inflation. Now you notice that I put that into the title, adjusted for inflation. So this is just gross revenue. This is adjusted for inflation. It's really important that you make a point, you highlight those kind of changes that you made. Now, one of the things you have to do when you're thinking about misleading with visualizations, you have to think about data. You have to think about the data and particularly outliers and missing data and data errors. And so we're going to go through a little exercise now where we'll use the Blakely Tires data to demonstrate some of the techniques you can use in Excel to find missing data, data errors, to really evaluate the data. So, like I mentioned last week, this is out of chapter 9 in the textbook. So you want to go to the textbook, find chapter 9, actually section 9.1, and find the Blakely Tires data, which you can download from the textbook, and download that. So what I want you to do is I want you to pause the video while you go collect that data, download it, and then open it in Excel. Now, I'm not going to pause, but you should pause while you're collecting that data. What I'm going to do is go to Excel where I already have downloaded the data. And here's the data. Here's what it looks like. It's got an ID number. Each row in this data is a tire, an individual tire. So here's its ID number. Here's where it was on the automobile. Here's its life in months. Here's its tread depth, and here's its miles. And so this is presumably tread depth and miles at the end of at the time they took the measurement. So we have one row representing a tire, where it was mounted on the car, so on and so forth. So what I'm really interested in this data, learning from this data right now, I'm in data exploration right now. So what I'm really interested in is things like, are these reasonable? Are there any outliers? Are there any blanks for that matter? So if you go to that section of the book and you follow through the instructions, you get all the instructions for doing this. I'm going to go through these quickly, and I'm just going to highlight a few Excel tricks that you might not be aware of that you can use. The book tells you explicitly how to do this. The first thing you do is you put these labels in: number of missing values, mean, standard deviation, minimum, and maximum. By the way, the book doesn't tell you exactly this order, but that's what you end up doing. Then you also put life of tire, tread depth, and miles in these columns, H through J. Now, if you're really astute, you notice those are exactly the same as this. And so I could just copy these with a Control C and paste them here. Now, so right now you have an empty graph. Again, pause the video if you're not keeping up. Go ahead and keep up. You've got a table with these uh, legends around the outside, but you don't have it filled out. So how do you fill it out? Well, the first thing is you want to count the number of blanks. So this is number of missing values. A blank would be a missing value. So we're going to use an Excel function called count blank, sort of like count. I'm going to sort of like count blank, and we're going to use it on the cell range. This data goes to 457, row 457. So we're saying count blank from 2 to 457. And we notice that there's no blanks in here. So that's good news. There were no blanks in the life of tire. So that's we can check that off and say, okay, life of tire is in good shape. Now, one trick you can do is that you can just drag this. So this formula, because of the way Excel works, this formula will just adjust. And so if I just drag this across, if I look at this one, it's gone to D2, and that's why that's D2, which is what I want. That's why I had these in the same order. That's why I had life of tire, tread depth, and miles in the same order in this table, because then it was just easy to drag those across. Likewise, on miles, it just picked up E. And by the way, you can click this, and it will show you what cells it's referring to. Okay, so in miles, we do have a blank. And if we scroll down here long ways, you can find it. Now I've done a special trick here to get that to highlight. The book also tells you how to do this, and here's the trick. You pick all of these that you're interested in, and you say conditional formatting, this guy right here, and you say highlight cell rules, and you say, in my case, I'm sorry, you say new rule. And in my case, I said format all cells based on their values. Sorry. I said conditional formatting, manage rules. There we go. I said on this selection, any cell that contains a blank value, so that I chose that out of the pick list, format it into this color. So you just follow the instructions in the conditional formatting, and anywhere there's a blank in all this, you get a highlighted cell. And so what happened was I got a highlighted cell on this particular tire. So this tire has a blank cell in number of miles. That's a problem. And you have to decide what to do with that. You know, a lot of times what you do is you show averages, and this would be a problem in an average. And so you have to decide whether you're going to exclude that tire altogether, or you're going to exclude that from the miles, or various things. When you go to try to plot that, sometimes that gets treated as a zero. Sometimes it gets ignored altogether. There's all kinds of different things that happen. But the bottom line is you have to understand where those are, because that's not real data. You have to understand where those are and do something about those. By the way, the last lecture where we talked about um, factorial data and data that's factors and data that's numeric. So these are obviously all numeric. This is a factor. So this can only assume, position automobile can only assume one of presumably four values. Maybe spare might be on there too. That wouldn't make sense probably. Right rear, uh, right front, left front. So this is a factor variable or a categorical variable because it can only contain one of four values. So I could actually tell Excel to sum this and I'd get some number that would be meaningless. Okay, so I found one missing value, and what I have to do is I have to decide what to do with it. I might say, you know what, I've got enough data here. I'm going to just delete this. Now, I wouldn't just willy-nilly delete rows that have blanks in them. You need to really think about that because sometimes there's a lot. And so you really need to think about what you're doing here relative to data when you do that. Okay, so we did a data exploration to find missing values. Now we want to understand what the mean is and what the standard deviation, what the minimum and maximum is, so we can find outliers. Okay, so for the mean, here's the calculation. It's called average. So average generates a mean in Excel. And again, I'm using that same range from C2 to C457. So that formula is calculating the mean of the life of tire. So the mean or the average of, well, the mean of life of tire is 23.76. And again, I just dragged that across. I just dragged this formula across, and I got this, which is the average of D, column D. And it says that the average tread depth was 7.64, and the average miles, I did the same thing, was 25,818 and 0.24. So, excuse me, that fast, that simple. I got the mean. Now, the mean is important because then I can see how far outliers are from that. Standard deviation is telling me how much variance I have. 31.3, oh, sorry. The formula in Excel is std.s. There's all kinds of different standard deviations. You can do in Excel. We're using the .s, and we're going from C2 to C457 again. So once again, I put that formula in, then I just dragged it across to these other two, and I got that the standard deviation on tread depth was 2.51, and the standard deviation on miles was 24,167. That's a huge number, right? So the miles varied a huge amount from one tire to the next. Okay, then I want to calculate a minimum because I want to see where the minimums are. And I used a formula in Excel called min from C2 to C457. Once again, there's the range. And then I just drag that across, and the min for tread depth was 0. So there are some tires in here where the tread depth is 0. That's probably something I should look at. It could be correct, but I should understand whether that's a incorrect value or a series of incorrect values, or it's something, or it's legitimate. And the miles of 206, that's probably reasonable. This set of data, the tires could have 206. Now, how do I find that tread depth? Simple way. You just go over here and you say sort, which is in the data function, say sort, and I want to sort on, make sure this checkbox is checked because I do have header rows, and I want to sort this on, let's see, sorry. I want to sort this on tread depth. I'm going to sort on tread depth, and okay, we'll go smallest to largest. And so you notice that there is one tire that had a tread depth of 0. That's possible. It seems kind of unlikely, although there are some that are 0.2. So again, I just want to investigate that. I want to understand if that's a legitimate reading or if it's an error. In this case, it looks like it may not be, but you really want to go back to the source data and figure out whether that's true or not. Okay, and then finally, let's see. So that was the minimum. And again, so I could do the same thing to look at the tires that had this minimum mileage. So instead of tread depth, I could sort on miles, smallest to largest. And yeah, I can see there's a lot. There's several that are 206, then there's 356, so on and so forth. Okay, and then the final calculation is maximum, and that is an Excel formula called max. And again, I'm just selecting that range using the max formula, and then I'm dragging that across. And so I see the maximum life of the tire was 601 months. The maximum tread depth was 16.7, and the maximum miles was 107,000. may be legitimate. I'd have to know the data, better to know whether that's legitimate or not. But the point really, in a vacuum like this, you can't really say whether these are legitimate or not. But you would understand the data more so than what we're understanding, just in terms of a just a sample data set, and you would know or be able to investigate whether those were legitimate values. And so that's a way of doing early on data exploration in Excel without visualization to find these kind of outliers. The outliers are really the big deal, and you have to pay attention to outliers. I'm going to talk in a future lecture about how outliers can be deadly. Okay, so you can go back to, or you can quit on the Excel for now. We're going to go back to this guy. So we did all this. Now, not all, whoops, sorry, I'm just trying to drag this out of the way. Not all extreme data are errors, but here's how you can identify whether you have errors that maybe are not extreme, but they're probably errors. And that's by doing a scatter diagram. So you can build a scatter diagram of the data. The book tells you how to do that. We're not going to do that right now, but the book tells you how to do that. And tread depth versus miles. And you can see that there are some data points that are way out. Now, this is a way of just visualizing these and saying, wait a minute, these maybe don't make sense. I've got a really high tread depth for a tire that has traveled 20,000 miles, whereas all the other ones have pretty a different tread depth. And I've got a really high mileage with a relatively low tread depth. So these could be outliers. And so again, it's something you want to investigate. And the way you would do that is you'd do a scatter diagram of miles versus tread depth. We're not going to do that for this exercise. We are going to do some scatter diagrams later. So let's talk a little bit about bias data. Bias data occurs when you have non-random samples. It's one of the foundations of probability and statistics is random samples. When you have non-random samples, it basically throws everything off. And there's various ways that you can introduce bias in your choice of data points. So let's just back up a little. So what we're doing is we're observing something that happens in nature, in the real world. So it might be, number of bacteria on a sampled surface. It might be tread depth. It might be, sales in the month. All kinds of different things. But what we're doing is we're taking observations at particular places and times. And if what we're trying to do, if we're trying to go from, if we're trying to use probability, we're trying to take a small sample and infer things about the whole population. So maybe that's the whole population. Maybe that the 457 tires in Blakely was the whole population of tires, but there might be millions of Blakely tires, and they just chose these to sample to get a reading. And so what they could be trying to do here is infer things about the larger population, like what the average tread depth should be given a certain number of miles. When you do that, if that's what you're trying to do, you want to take a random sample. So you introduce selection bias sometimes but without understanding it. So as an example, you do political polling and you conduct it on a landline phone. In other words, you call people that have a landline, and you're going to miss people. You're going to miss people who don't have landlines. And today, that's a lot of people. And it tends to skew age demographically. So older people tend to have landline phones, younger people tend not to. And so if you're doing political polling based on landline phones, you probably are not getting a random sample. Simpson paradox is an interesting one. It's a type of selection bias, and it occurs when samples are pulled out of the whole sampled collection. And we'll talk about, I'll give you an example of that in a minute here. And survivor bias is when the sample consists of disproportionately large number of observations corresponding to the outcome of a particular event. It's like it implies survivor bias. Let's talk about those individually. So symptoms paradox, there's a data file in your book 9.2 called Angel Income. Again, we're not going to, in this course, or sorry, I'll say it differently. In this recording, I'm not going to do this work. You can do this work, and I might recommend that you do, uh, to demonstrate this. And so what we did was we used Excel. We built a scatter diagram of the location and compared it to the scatter charts where they were aggregated and where they weren't. And what you get is you get two different charts. Now let me explain the charts. So we took out of that data set, we plotted annual income versus age out of the whole data set, and we got a chart that looks like this. Now, one thing we're going to talk about is this idea of introducing a trend line, trying to find a trend in the data. And this is probably a least squares fit line, which means that it's the line that has the is the lowest value of the square of the distance from the line for all the points. And so the real point here is that it's downward, which means it's negative, and it's, pretty dramatic. And so what that means is there's a negative correlation between age and annual income. And so that intuitively makes sense. As you get older, particularly beyond 40, your income tends to go down. So, well, maybe it doesn't make sense. Actually, your strongest earning years are between 40 and 60, as it turns out. So this is actually counterintuitive. So when I look at the whole aggregated data, that's what I get. However, if I take it apart, so this was three different cities, San Francisco, Dallas, and Naples, Florida. And when I take it apart and I look at the individual cities, San Francisco, Dallas, and Naples, I actually get a positive trend on all three of those. And so what's happened is that by mixing the cities together, which have vastly different incomes, I get this misleading statistic on what happens to income as you age. So just to refresh here, age is the independent variable, which means that's kind of the one you can change. You can't change your age, but you can change how you what you select. And income is the dependent variable. And so we're saying if I chose a certain age, 60, then I would expect, if I had a new reading, I would expect the income to be around $70,000. So it's pretty interesting. This is Simpson's paradox. What this is saying is that if I have a big and broad enough spectrum of people where they have vastly different income levels, then I can actually drag the whole thing in this direction when in fact, this is more like the direction I would expect. I would expect the slope line to go up to a point. I would actually expect it to drop off after 80, but I'm drawing a linear line as opposed to a curved line, as we talked about last time. So in this case, they keep going up. That's not really true, right? After about 65, everybody's income tends to go down. Not everybody's, but most people's income tends to go down. So by taking it apart into the different cities, I have actually shown a much more realistic example of what's going on. Simpson's paradox, that's called. Survivor bias. This is the typical example they use for survivor bias, and it's where the term was invented, and it's pretty intriguing. So in World War II, they were very interested in which planes got shot down. There's a lot of air warfare, bombers, and a lot of dogfights in the air, that sort of thing. They're very interested in which planes got shot down, and so that what they did was they studied the planes that came back and they said, well, where have they been shot? And so they put a reinforcing metal in the places where they'd been shot, which it turned out was on the tips of the wings, kind of right in the fuselage, and on the tips of the tail. So a mathematician came along, Abraham Wald, and he successfully argued that that was exactly the opposite of what they wanted to do because these planes survived. In other words, these planes got hit, yes, but they lived to fly back. What they didn't do was they didn't go look at the crashed planes to see where they were hit. So this is a really excellent example, and it's where this term survivor bias came from because the planes that survived were the wrong ones to look at. They should have looked at all the planes or the planes that didn't survive, particularly because those were really the ones that they're most interested in. Now, there's all kinds of examples of survivor bias. It's particularly done when you want to influence people around stock picking because you pick a portfolio and you send it to 100 people. And sorry, you pick 10 portfolios and you send them each to 100 people. And 8 of the 10 are failures, but 2 of the 10 are successes. And so you go back to the people that you were successful with and you say, look what a great stock picker I am. You actually do that in several sequential steps, refining the thing each time. And by the end of it, you can look like a brilliant stock picker when in fact all you did really was you played the law of large numbers. You just kept uh, uh, different subsets, and the successful ones you kept, and the unsuccessful ones you threw out. So here's an example of survivor bias, and it has to do with the risk tolerance comparison of entrepreneurs and non-entrepreneurs. And the problem with this was that uh, so what they're saying is that the entrepreneurs have a higher risk profile than the non-entrepreneurs. The problem is that the entrepreneur, so this is ones who were still entrepreneurs. And so the problem is that the non-entrepreneurs, the people who are entrepreneurs and quit being entrepreneurs quit. So they only got the more highly risk tolerant entrepreneurs. Okay, we saw in the earlier example adjusting for inflation, and here's a example of adjusting for inflation using price gasoline. This is pretty involved. Your textbook goes through this. Again, I'm not going to do that in this lecture. You can do that from the textbook. There's lots of calculations here, which I'm not going to go through. But what I am going to go through is the visualization that you get for that. And so this is comparing nominal versus inflation adjusted gas prices. So this is the national gas price, and you see what happens is the gas producers could say, well, it's I've been pretty good. I've been pretty disciplined. But if you take the inflation adjusted gas price, you see it's gone way up. So and by the way, it depends a lot on what you choose as base year. So inflation adjusting, whenever you do adjusting like this, you pick a year and you subtract that out of all the values. And so the year that you choose as the base year really influences how this visualization looks. Now, one of the major sins of graphing is a pretty easy one to make, although most graphing software won't let you do this, and it's for a reason. And it has to do with where the zero axis is. So whenever you have a filled chart, which could be a bar chart like this, or it could be a density graph or something like that, where you're showing the area below as filled in, it has to start at zero. It just has to start at zero. And the reason is that if you don't start at zero, you can lie with it. So this is the majority of voters against the library levy. And so it says that, you look at this chart and say, wow, there's a lot more that are against it than are in favor of it. And by looking at this chart, that's what you would come to right away. You would pre-attendedly come to the conclusion that there's a lot more that are against it. However, this only goes down to 48. if I take this down to 0, there's a really small difference in the for and against columns here. Now, against is still higher, but it's higher by a really tiny amount. Now, this chart is the intellectually honest chart because this really lets me see that there's really not much difference between the for and against. So this kind of chart, whenever you have a chart that has the area filled in, it has to go to 0. Now, I could have drawn these as data points. So I could have put a point here and a point here, and then I could have left this at 48. Um, it's still somewhat misleading, but it's not misleading to the degree that where it was I see so much bigger bar. Another trick that you can play, for some reason, the climate deniers are masters at this, right? So this chart on the left is looking at the average uh, global surface temperature in degrees C, and a climate denier would say, "Well, see, it's barely moved at all. In fact, I can barely tell that that's going up between 1880 and 2020. It's hard to argue that that's changed at all." And here's the problem. The problem is with the scale. This goes from 0 to 50 C. 50 C is really hot. We're used to Fahrenheit instead of centigrade. I can't do that calculation in my head real quick, but it's really hot. And believe me, it's really, really hot. Here it is. If you properly scale the y-axis. Now, once again, this hasn't filled in. It didn't fill it in below, so I didn't have to go all the way to 0. And so what I did was I properly scaled it. And so, a reasonable scale is 135 to 145. And I'm sorry, 13.5 to 14.5. And what you see is it varies a lot, which you would expect. That's another thing that makes you suspicious of this. You know that the surface temperature varies a lot. You see that it varies a lot, but you also see that the long-term trend is definitely increasing and increasing pretty dramatically. It's hard to say that 1 degree or 2 degrees C is a big deal, but on a global scale, it's a big deal. Okay, so I wanted to talk about a visual of the day. We're actually going to have two of those. Actually, we're going to have a visual of the week later. This is out of the Boston Globe, just recently, March 4th, and it's looking at that same thing. Now, they did this differently. So this chart is just taking a point in time. So that's why it wiggles around so much. What they did in this chart was they took a 30-year average. And so what the way you do a moving average is that you take a period. In this case, they took 30 years, and they looked at 30 years of data, I think previously, and they took the average of that. And then they moved to the next year and they looked at the previous 30 years and took the average of that. And they did that again and again and again and again and again, which is easy to do because we have computers that can do it until this point. And this point was 24. They took 30 years prior to that. They took the average, and that's what the point is. And so what this does is it shows you that the 30-year average, that's why this is so flat, because I'm taking an average that smooths out. The advantage to a moving average is it washes out the minor fluctuations. And the period that you choose, a 30-year average is a long period to choose, and the period that you choose determines how much things get flattened out. So this is called a line graph. I'm sorry, this is called a slope graph. So I have a point here, and I have a point here, and I have inferred points in between. Probably what I have is one per year, and then I drew a line through it. Very often they're done like this. You put a data point at one significant point, and another data point at another significant point. This is representing, let's see. Yeah, it's representing 6 states: Rhode Island, Connecticut, Massachusetts, New Hampshire, Vermont, and Maine. So this is the average winter temperature, 30-year average winter temperature. And you notice in Rhode Island, it's gone from average of 31 to an average of almost 34. so on and so forth. So uh, slope graphs are getting more widely used. Now, what happens is that your audience is trained on certain visual forms. And so you want to use those where it makes sense because you're going to be able to communicate better with them. And so most of us know what a slope graph looks like. We may not know that it's called a slope graph, but we know what it looks like. We know what it's telling. And so pretty quickly by looking at this, I can tell what's going on. And that's the point. That's the point of almost all visualizations is let the person very quickly make an assessment of what they're seeing. This is called pre-attentive, and then help them understand specifically what you're trying to communicate. So, my opinion, I think this does a pretty good job of saying that, yeah, the average winter temperature is going up. Now, you can argue whether that's global warming or not, but the average winter temperature is definitely going up in these 6 New England states. Um, okay, here's another one. We're talking about this is global surface temperature again, and we're using a aspect ratio that tends to smooth stuff out. So when I put a pretty tight x-axis on this, I can pretty dramatically see what's going on. When I put a much wider x-axis on, it's not so dramatic. So aspect ratio has to do with the height and the width of the chart. And so when I stretch it out, so these are roughly even, right? Not quite, but roughly the same distance here as here. Not units because they're different things we're measuring here, but it's roughly the same distance. This from here to here, 1870 to 2020, is roughly the same length of line as it is from 13.5 to 14.5. Not quite, but it's close. It's almost a square. This one is not. This is probably 4 times longer than this one. And so it's another way of misleading your readers. I can't say it more politely. I can't say it more politely, so I just say misleading your readers. If you choose to do things like this, you're going to mislead your readers. And sometimes, very often, people do that for a reason. I mean, they do that purposely, and that's where we're just not being intellectually honest. Um, okay, so uh, I'm going to go on record as saying I don't like dual axis charts because they're hard to interpret, they're hard to understand. And so here's a dual axis chart, excuse me, that clearly does not work. And what we've got is we've got GDP and we've got unemployment rate. And the reason it doesn't work is because they try to keep the scales of the y-axis the same. So this is technically a dual axis chart. I think it is. No, maybe it's not. Maybe they're putting both of these on a single axis chart. In other words, going from 0 to 25,000. The problem is that GDP is in dollars billions and unemployment rate is a percent. So it goes from 0 to 100%. So of course, this line is not going to look like anything compared to this line. So this is not misleading. It's just wrong. It's just plain wrong. So the remedy sometimes for that is a dual axis chart. And so what you do is you put so it's when you want to do 2 data values, you put one of your data values on this left axis and one of your data values on this right axis. And so in this case, we put the GDP in billions going from 0 to 25,000. And then we put unemployment rate from 0 to 12%. So now the graph at least, makes sense, but it's really hard to interpret these. What you want to do is you want to read significance into when these lines cross, and there's no significance in that because I could just as easily have made this top value 23 or 15 or something like that, and that would change where these cross. And so the problem with dual axis charts is exactly that. If they're not the same units here, and you'd only go to a dual axis chart if you had that case going on. As humans, as mere mortal humans, we really can't interpret what this graph is trying to tell us. So instead, what we do is normally you want to split those up. You want to just put 2 graphs. And a lot of times, next to each other, left to right is best. Sometimes top to bottom is best. But this gets people out of trying to interpret where this orange line crosses this blue line. It makes them understand, it helps to make them understand that these are two much different axes. Okay, so they're calling these temporal frequencies. That's just simply the length of time that you choose for your moving average. So this is shown, I'm going to correct that. Temporal frequency has to do with how often you take a reading. So this is taken 365 per year, or they're taking a reading every day. So the lines aren't, well, actually, no, they are every day. So the lines are, moving around every day, up and down, up and down, up and down. So here's the same chart, but we're only taking a reading 6 per year. So we're only taking a reading every other month. And so you notice what happens is that tends to wash out all these up and downs. And if I'm looking for the overall trend, that can work pretty well. So there is not necessarily is one of these right and one of these wrong. It's just a different way of thinking about the data, different way of visualizing the data. And you, as the designer of the chart, gets to choose. Okay, in geographic mapping, you have lots of opportunities to misread users. And so this is estimated number of people living in poverty by state, and this is just a raw number. And of course, the problem with that is that the population of some states is dramatically, well, in all states, is dramatically different than other states. So California and Texas and Florida have huge populations, so of course they're going to have more people. Well, not of course, but it would be likely that they'd have more people living in poverty. So of course they're going to be lit up in a darker shade of blue or darkened in a darker shade of blue. This is not wrong. It's not incorrect, but it just doesn't tell me what I need to know. It's just not informative. This chart instead is it's saying poverty rate. So they're taking the number of people in poverty, dividing it by the population. And so you notice it goes from 7.3 to 19.1. Now I have a much more meaningful chart. So now you notice that New Mexico and some of the states in the South are the ones that are lit up the most. And this is a much more meaningful chart. Okay, another think session. I want you to pause the video and consider these three studies. 1930s, Dr. Joseph Rhine tested 500 participants to guess the order in a shuffled deck of cards. Only those participants who guessed correctly moved to the next round. The last participant to guess right every round was declared to have telepathic abilities. Pause the video and think about that. I'm going to do these one at a time. Think about that. And the question is, uh, there's some bias in this. And what kind of bias is this? Selection, Simpson's paradox, or survivor? I want to encourage you to pause the tape. I'm not going to. This is a great example of survivor bias. Okay, so the people who guessed incorrectly didn't survive. So the survivors, the survivors, I guess, moved on to the next round. And so he just kept refining it. And by the end, he said, this person had telepathic abilities. No, they didn't. They were just lucky through the 10 rounds. I'm not sure how many rounds there were. I'm not sure how many rounds there were, but they were just lucky through all the rounds. So that was an example of survivor bias. Okay, number two, a policy group lobbying for the alcohol industry conducted an exit poll outside a popular restaurant late at night. The restaurant patrons were asked whether driving and drinking was a serious problem. The policy group concluded that driving after drinking is not a serious problem. Pause the video again, please, and think about whether that's a example of selection bias, Simpson's paradox, or survivor bias. I'm not going to pause. Um, this is selection bias, right? Of course, you're going to get people who are uh, uh, inclined to say driving after drinking is not a serious problem. Of course, you're going to get people who say that as they exit a popular restaurant late at night. High probability they've had some drinks, and so they really don't think it's a big deal. So this is selection bias. I chose the people who would give me the answer I wanted. Okay, third think session, a research group followed for 40 years a cohort of individuals. The study's main conclusion was that those who drank red wine were richer, better educated, had lower levels of cholesterol, and consequently a lower risk of heart attacks than those who did not. Pause the video again, please, and think about selection bias, Simpson's paradox, or survivor bias. I'm not pausing again. Actually, I'm going to pause for a minute. Uh, so this could be one of two. So it's not Simpson's paradox because we haven't we don't have enough data here to say, and there's not different groups in this, so it's not Simpson's paradox. It certainly could be selection bias. In other words, they how they picked the group, but it's really about survivor bias. And so uh, if they studied people for a group of people for 40 years, some of those people died. So this is a, clear cut survivor bias. So they looked at the ones who didn't die and they said, oh, the ones who didn't die drank red wine were richer and better educated. Well, wealth goes with longevity. It just does. Worldwide, that just happens. And so this is a survivor bias example. Okay, so in this lecture, we identified missing data and data errors using Excel. We learned about bias data. We learned how to adjust for inflation. Well, we didn't necessarily learn how, but we learned how you could do it in Excel. We learned different ranges of values for the x-axis can have, or for either axis can have, a significant effect on how people perceive the graph. We learned about dual axes charts, which again I don't like. We learned about selecting time series, which can change the insights, and how to present misleading the audience when using geographic maps. That's only we didn't learn generally how to do this. We learned one specific way. Okay, I wanted to take you through. Yeah, we got just a little bit of time here. I want to take you through this video. So if you download the slides, this link will take you to the same thing I'm going to show you. A fascinating bit. So in the last lecture, I talked about why we're at where we are, and one of the things was I said this technology explosion having to do with data, with the ability of devices to collect data. And so this article is about how your privacy is dramatically invaded. So let me just pause for a minute. Imagine that well, since we got a new administrator, Elon Musk comes along and he says, "Congratulations, everybody! I'm going to track every movement you make, and all you have to do is wear this wrist GPS device, and it will send via satellite to a central server the government controls your location, and I'm going to track everywhere you go because I need to know that because I'm Elon Musk and I need to know that." There'd be riots in the streets. There may be riots in the streets anyway about that, but not about that. But yet we do that every day. When you carry your cell phone around, you do that every day. Uh, uh, any anybody, not anybody, but anybody with access to that data can track your location, and that data is pretty generally available, not to you and me, but to people who have the time and the resources, particularly the money, to buy that data because they're interested in it because they want to know where you go. So this is talking about uh, cell phone tracking. So here's a beachfront neighborhood in Los Angeles, and it's lighting up the cell phones that they tracked. Here's the Pentagon. It's lighting up the cell phones that they tracked. Here's the White House, lighting up the cell phones that they tracked. Here's Mar-a-Lago, tracking cell phones. Um, and so the point is, that's what this article is about, One Nation Tracked, and it's pretty interesting. Let's see, let me go down here. Yeah, here we go. Okay, so they took, out of all the data they got, they took all the cell phones they picked up on a particular date, 10,000 smartphones that were tracked in Central Park. Then they took one smartphone and they isolated it from the crowd right there. Then they followed that person around. They saw where that person went. Here's all the pings from that smartphone over the period covered by the data. I don't know what the period was. So you can see every single location that that person visited over that period. Um, you can connect the pings together. You can superimpose roadways on that. You get a real diary of the person's life. Let's see, we have more of these. Anyway, fascinating article, I think. Just a absolutely fascinating article. They have various other locations. That's Beverly Hills. This is San Francisco. So my point earlier about device data and tracking you everywhere you go, here's a prime example of it. It's really quite uh, frightening in my mind. I'm not sure if you should be frightened or not, but I'm pretty frightened of it. Okay. Okay. So for this week on Friday, you have a couple of questions. So you're asked to read chapter 1 and chapter 9. And then you have a couple of activities. One is to install Tableau in Excel. You probably have Excel installed already, but you need to install Tableau also. There are instructions in Canvas on how to do that. And you have a discussion board. So introduce yourself, please. Excuse me. Due Sunday. So you're going to make a posting about yourself on Friday, and by Sunday, you need to respond to at least two of your classmates' posts. So it's pretty simple this week. Just a heads up, 2 weeks from this Friday, not this Friday, but 2 weeks, I'm giving you an advance warning. You need to have selected data for your final dashboard project. Now you can learn about the dashboard, about what the requirements are, if you go look at the term project posting requirements, which you can find in Canvas. Basically, you have to produce 4 different types of reports. You'll learn about, I'm sorry, types of graphs. You'll learn about what those are as we go along, and you'll learn what a dashboard is. But what you're looking for right now is data for your dashboard project. So you want to read that assignment, be thinking about what kind of data you could use for your dashboard assignment. And we'll see you next time.